Hello everyone, today we're diving into some new AI breakthrough projects that announced recently in GitHub. First of all, something that could revolutionize how we create digital avatars. Imagine being able to generate a lifelike 3D model of yourself from just a few selfies, or even a single photo. Well, researchers have developed a system called HeadGAP that aims to do exactly that. Let's break it down. Imagine you're designing your character for a new VR game. Instead of choosing from pre-made options, you simply upload a selfie and boom, there's a 3D avatar that looks just like you, able to make all kinds of expressions. Sounds like sci-fi, right? Well, it might be closer to reality than you think. HeadGAP, short for Few Shot 3, D-head avatar via generalizable Gaussian priors, is a new AI model developed by researchers from ByteDance and Shanghai Tech University. In a nutshell, it's a system that can create high-quality animatable 3D head avatars from just a few images, or even a single image of a person. So how does it work? Well, HeadGAP uses a two-phase approach. First, there's a prior learning phase, where the AI learns general characteristics of human heads from a large dataset of 3D scans. Then, in the personalization phase, it applies this knowledge to create a unique avatar from a small set of input images. The key innovation here is the use of what they call generalizable Gaussian priors. This technique allows the AI to capture the essence of what makes a head look human and realistic while still being flexible enough to adapt to individual features. One of the coolest aspects of HeadGAP is its ability to animate these avatars. Once created, your digital double can smile, frown, or make any expression you want. The paper shows examples of avatars recreating various expressions and even being viewed from different angles. Now, this technology is pretty exciting, but let's think about its real-world implications. On the positive side, it could be a game changer for industries like gaming, VR, and film. Imagine creating custom characters for games without needing expensive motion capture equipment, or quickly generating digital doubles for visual effects in movies. There's also the question of accuracy and representation. While the examples in the paper look impressive, we need to see how well it performs across a diverse range of faces and skin tones. AI systems have struggled with bias in the past, so it's crucial that technologies like this work equally well for everyone. In terms of current limitations, the paper doesn't go into detail about how the system handles things like glasses, facial hair, or unusual hairstyles. These could be potential challenges for real-world applications. Overall, HeadGAP represents an interesting step forward in the field of 3D avatar creation. It's not quite at the point where you can just snap a selfie and instantly have a perfect 3D model, but it's getting closer to that reality. As with any AI technology, it's important to approach it with both excitement and caution, considering both its potential benefits and possible drawbacks. Next, let's take a look at Video Face Restoration AI model. Imagine watching an old grainy video of your grandparents and suddenly being able to see every detail of their faces in crystal clear quality. Well, that's exactly what this new technology aims to do. Let's dive a bit deeper into what makes Keep tick. The researchers at Nanyang Technological University have tackled a persistent challenge in computer vision: how to effectively restore low-quality face videos while maintaining consistent, high-quality details across all frames. Previous approaches to this problem typically fell into two categories. Some adapted general video super-resolution networks to face datasets, while others applied face-image super-resolution models to each frame independently. Both methods had their drawbacks, either struggling to reconstruct facial details or failing to maintain temporal consistency. Keep takes a different approach. At its core, it's all about maintaining a stable face prior over time. In AI terms, a prior is the model's understanding of what a face should look like based on its training data. But here's where it gets interesting. Keep doesn't just use a static prior. It dynamically updates this prior as it processes each frame of video. To achieve this, Keep leverages principles from Kalman filtering, a technique you might be familiar with from GPS systems or robotics. Kalman filtering is all about estimating unknown variables from a series of measurements over time, even when those measurements are noisy or inaccurate. In Keep's case, it's estimating the true appearance of a face from a series of low-quality video frames. Each frame provides new information, which Keep uses to refine its estimation. Technically speaking, Keep operates in the latent space of a pre-trained face super-resolution model called CodeFormer. It recurrently updates the current latent state by incorporating information from preceding frames. This is done through a custom Kalman filter network, which includes a gain network and an uncertainty network. The gain network determines how much to trust the new information from the current frame versus the prior estimation from previous frames. The uncertainty network helps quantify the reliability of the current estimation. Keep also incorporates a module called cross-frame attention, or CFA. This allows the model to align and aggregate features across multiple frames, further enhancing temporal consistency. What's particularly clever about this approach is that it allows Keep to handle severe video degradation more robustly than single-image models. It's also shown improved performance on non-frontal faces, providing more stable estimations of face priors from different angles. So in essence, Keep is constantly learning and refining its understanding of what a particular face should look like as it processes a video, frame by frame. This results in restored videos that not only look good, but maintain a consistent, natural appearance throughout. Here's the cool part. Keep doesn't just process each frame in isolation, it actually uses information from previously restored frames to guide how it restores the current frame. This helps keep facial details consistent from one frame to the next, avoiding that weird, flickering effect you sometimes see in AI-enhanced videos. The researchers tested Keep against other state-of-the-art methods, and the results are pretty impressive. They're reporting a 0.8 decibel improvement in PSNR, which is a standard way of measuring image quality. More importantly, the restored videos show much better temporal coherence, meaning the face looks consistent and natural as it moves. Now let's think about some real-world applications. Obviously, this could be huge for restoring old films and home videos, but it could also have applications in video conferencing, especially in low-bandwidth situations. Imagine being able to have a clear, detailed video call even with a poor internet connection. And the last one, this is exciting for me. Sketch to 3D. Imagine sketching a quick doodle of a game world, and boom, it transforms into a fully realized 3D environment you can explore. Sounds like magic, right? Well, that's exactly what researchers at Tencent and the Australian National University have achieved with their new Sketch2Scene model. Now let's get into the nitty-gritty of how Sketch2Scene works. This AI pipeline is tackling a major hurdle in 3D content creation, the lack of large-scale 3D scene datasets for training. Unlike object-level 3D generation, where we have datasets like Objaverse XL, there's no equivalent for entire game scenes. So how does Sketch2Scene get around this? The secret sauce is in their clever use of 2D diffusion models. Here's the breakdown. User input. It all starts with a simple hand-drawn sketch or text description from the user. This is where you outline your vision for the game scene. 2D isometric generation. Instead of jumping straight to 3D, the system first generates a 2D isometric image. They're using a modified version of ControlNet, a conditional diffusion model, to do this. The isometric view is key here. It gives a consistent representation of the scene without worrying about camera angles. Visual scene. Understanding. This is where things get really interesting. The system analyzes the 2D isometric image to extract crucial information. It segments the image into different components like terrain, objects, and structures. It generates a height map to understand the terrain elevation. It creates texture splat maps to define surface materials. Procedural 3D generation. All this extracted data then feeds into a procedural content generation engine. Think Unity or Unreal. This is what turns the 2D concept into a fully realized interactive 3D environment. What's particularly clever is their use of a base map in painting technique. This fills in parts of the terrain that might be obscured by objects in the 2D image, ensuring a complete 3D landscape. Now let's talk real-world applications. For indie game devs, this could be revolutionary. Imagine sketching out a level concept and having a playable 3D prototype in minutes instead of days. It could drastically speed up the iteration process in game design, but it's not just for games. This tech could be valuable for rapid prototyping in architecture, urban planning, or even film pre-visualization. Any field that needs quick 3D environment concepts could benefit. However, we need to keep some limitations in mind. While this is impressive, it's not going to replace skilled 3D artists and level designers anytime soon. The output, while good for prototyping, likely won't match the detail and optimization of handcrafted environments. There's also the question of control and customization. How much can you tweak the final output if it's not quite what you envisioned? The paper doesn't go into detail on fine-tuning options, which could be a crucial factor for practical use. Another consideration is the reliance on isometric view. While great for certain game styles, it might limit the types of environments you can easily create. Complex vertical structures or highly detailed interiors might be challenging to represent accurately. One particularly interesting aspect is the use of isometric projection. This simplifies the 3D understanding problem, but it also limits the types of scenes that can be easily represented. It works great for certain game styles, like strategy or simulation games, but might be less suited for first-person or more vertically oriented environments. The researchers have made some smart, technical choices to overcome data limitations. Their use of a pre-trained 2D diffusion model combined with specialized training on isometric game-style images allows them to leverage existing AI capabilities in a new domain. Looking ahead, I'm excited to see how this technology evolves. Could we see it integrated into game development tools? Might it expand beyond isometric views to handle more diverse scene types? And how might it combine with other AI tools for content generation? What do you think about this technology? Which project mentioned in this video are you looking forward to? Let me know in the comments below. Don't forget to like and subscribe for more AI tech updates. Until next time, see you in the next video.